Hi, I'm Tracy Dean with the U.S. Army Combat Capabilities Development Command's Army Research Laboratory. Welcome to What We Learned Today, a podcast where we talk with Army scientists and engineers about the science and technology that will modernize the United States Army and make our soldiers stronger and safer. Today, I talk with Dr. Peter Reynolds, the Army Senior Research Scientist for the Physical Sciences at the Army Research Office, an element of the laboratory. As an expert in the field, his focus is in condensed matter physics, theoretical chemistry, atomic and molecular physics, and quantum information science. Reynolds earned his doctorate in theoretical physics from MIT in 1979. He is a fellow of the American Physical Society and has held visiting appointments worldwide. His publications have been cited more than 2,500 times. Peter, welcome to What We Learned Today.
Thank you. It's my pleasure to be here.
So your background is in theoretical physics, statistical mechanics, particularly phase transitions and critical phenomena, but you manage programs in atomic and molecular physics. Can you tell me how that came about?
I'd love to tell you about that, but please bear with me because it's something of a tale. So, as both an undergraduate and a graduate student, I was fascinated by statistical mechanics, by how what was to me really weirdly complicated and non-intuitive ideas in thermodynamics just dropped out of this really clear and simple microscopic picture that's statistical mechanics. And I particularly became fascinated with phase transitions, which are abrupt changes of behavior that are what's called mathematically singular. Basically, that means having infinities in their description, but they could be explained by this theory. And around the same time, the renormalization group was being developed, and that too was really satisfying, and it explained singular behavior, something that traditional mathematics had difficulty dealing with. And in addition, I've always been interested in magnetism from childhood. And this new theory was really ideally posed to address questions in magnetism and in phase transitions in general. And I was becoming interested in disorder. And I put it all together in a renormalization group theory for disordered spins. And from that, I went from disordered magnets to percolation. So the approach I created was very intuitive, but the equations were getting out of hand. So I then developed the Monte Carlo method to do the renormalization group, something that was entirely new at the time. I loved percolation and the clusters that it formed, and I got into fractals and fractal clusters. And to get support for that line of research, which was brand new to my advisor, I worked with him in writing a grant proposal to ARO, of all places, and it got funded. So it made sense for me years later to come to ARO, but right. I'm kind of getting ahead of myself.
Right.
So first I took a position at Lawrence Berkeley Lab, and I did what was effectively molecular physics. And I got funded for that work through the Office of Naval Research, which is ARO's counterpart at the Navy. And after some years of doing that work, which was very interesting, I learned that my O&R program manager had moved on. He'd actually become like a division chief. And I was also looking to move back east for personal reasons at that time. And so I was encouraged to apply for his position. And it involved atomic and molecular physics and the physics of clusters. So I had a couple of those pieces already. And I had previously studied those clusters. They were fractal clusters in the context of percolation. So the thing I was missing was atomic physics. And being a theoretical physics, I figured that wouldn't be hard to learn. But in fact, it was really very different from everything I'd already known. It turned out to be just exciting, though, and it took a little while to get up to speed. But it was really great. It was really fun, and it was enormously satisfying. In managing that program, I began to see that the forefronts of that field, of atomic physics in particular, were evolving where there could be convergence to my older interests in statistical physics. Things like Bose-Einstein condensates and quantum degeneracy, Mott transitions, which is a type of phase transition, optical lattices, which connected to my spin lattice models, Hubbard models and Ising models, which are particular examples. So I pushed the frontiers in atomic physics in those areas because they were exciting to me. But they also had clear connections to DoD interests. For example, the master clock at the Naval Observatory. That clock is obviously, that keeps master time for all of DoD, and is what GPS is synchronized to. So this atomic physics, these ultra cold atoms that led to these phase transitions, were what enabled these better clocks. In fact, these clocks are now being used at the Naval Observatory. So this direction was really very successful, and it led to a handful of Nobel Prizes and even an invitation for me to go to Stockholm. So in the process, we were uncovering the beginnings of a new field of science as well. So that really made this interesting, and that's the field of quantum information science. So that takes us full circle to where I am now. So that's how it all came together.
Great. Thank you for explaining that to me. So theoretical chemistry seems a bit far afield, yet you spent 10 years working as a chemist. Can you tell me what you did and how that connected with your background?
Right. So that really seems, you're right, totally different from everything I just described to you. What I'd done in grad school, the statistical mechanics that I told you about, that was all classical behavior. And I'd always fancied quantum physics for its really non-intuitive behavior and its paradoxes. So when I went to Lawrence Berkeley Lab, I joined a group of theoretical chemists. And I applied my Monte Carlo expertise that I had used in the renormalization group approach for studying phase transitions. And I used it there to solve the Schrodinger equation, which is the equation that describes the quantum realm. That approach, using Monte Carlo for solving the Schrodinger equation, is now known as quantum Monte Carlo. And it was a natural fit for me and my background, but you're right, a vastly different area of science. And working with this group, I learned about traditional ab initio theoretical chemistry methods that they were using, and also what was then an emerging approach called density functional theory. It's now very, very well known and is replacing many of those ab initio approaches.
You're now widely known for your role in shaping quantum information science. This seems entirely different from all the things you've done before. How does this fit in?
So as I mentioned earlier, quantum information science was an outgrowth of my atomic physics program at the Office of Naval Research. I had funded a lot of the early work in laser cooling, which was foundational for the early work in what became quantum information science. A lot of it also grew out of what's called precision metrology, which is science of measurement. And that was largely an atomic, molecular, and optical physics enterprise that field does a great deal in precision metrology. So it was an area that I was responsible for. And in fact, I mentioned the Naval Observatory and the Master Clock, and that's an aspect of precision metrology. But out of that work, out of funding the science behind these ultra-precise clocks, they were based on atomic ions trapped in what were called Penning traps or RF traps. But out of that work with those trapped ions came the very first quantum bit. So we went from precision metrology, which was work done at NIST for these atomic clocks. We went to the beginnings of quantum information science. Then these trapped atoms, they were put into arrays that were called optical lattices. It's basically the light fields, the maxima and minimum of the light interfering cause these areas where atoms actually get trapped. And so now we had an analog of these spin lattices that I had done as part of statistical mechanics in graduate school. And we now had a way of doing a simulation, a quantum emulation, if you will, of these models that as a grad student I had actually done theoretical research on. So that's sort of quantum information science was an outgrowth of my atomic physics program, but it also connected to that work that I had done in grad school.
So tell me, what was the spark that ignited your passion for quantum information science?
Well, I think it was when I heard about quantum computing, actually even earlier, when I first heard about quantum mechanics. The laws of quantum mechanics are so bizarre, and I love that. They're really strange and paradoxical. And then I heard that there were these ideas that dated back to the 1980s from Richard Feynman that one could use quantum mechanics to build computers, use the properties of quantum mechanics rather than classical physics, and that could potentially lead to far more powerful computers. And then in the mid-1990s, a man named Peter Shor came up with an algorithm now very famous for being able to solve an incredibly hard mathematical problem, which is prime factorization. And that was mind-boggling to me.
Now, would you like to elaborate on why it was mind-boggling to you?
That you could solve a problem that was impossible on a regular computer. It's not just you're speeding something up. You're basically taking something that's impossible. NP problems scale exponentially. That means that if I give you a large number to factor and you try all the numbers and maybe it takes you, an hour to do that, if I make that number just a little bit bigger, it will now take me a week to do it. And if I make that number just slightly bigger still, it might take several years to do. And I just add another couple of decimal places, and it takes longer than the age of the universe to do. That's what we mean by a problem that really a classical computer can't solve, because it scales so incredibly high with exponentially high. And that another kind of computer based on the laws of quantum mechanics could solve it. I mean, it's breaking all our fundamental understanding at the time of what we had of computer science. Mm-hmm. So quantum mechanics was already mind-boggling with its many paradoxes, but this was yet another aspect.
So where is quantum information science now, and where is it going?
Actually, the field has grown by leaps and bounds since its emergence, and it continues to expand rapidly even now. Starting off, as I said, in the 1990s, it was a small spin-off from atomic and molecular physics. And it's going on, and it began to have input first from other parts of physics, from condensed matter physics, and then even beyond condensed matter physics. And it's now spread to material science, to mathematics, to computer science, and most recently to engineering. After years of support through the Army Research Office, in 2015, we successfully pushed it as a significant program within ARL in-house. So it led to a program that specifically emphasized quantum networking and quantum sensing in particular. But beyond the Army and DoD, it got recognized internationally as a significant new field. Universities and industry, even worldwide, have taken note. It's actually, spreading, like I said, by leaps and bounds. In fact, recently, Congress passed the National Quantum Initiative Act that was passed in 2018, so just a couple of years ago. The Department of Energy got involved and stood up 5 new centers in the last few months. And NSF, who had already been supporting quantum information, stood up 3 brand new centers. And back here at DoD and in the Army, it's become a priority research area for both DoD OSD and Army in-house. And AFC in the recent guidance put it as one of the Army's 9 priority research areas.
The Army has a new way to fight and win in the future. I'm talking about multi-domain operations. So how does quantum information science fit into this?
Okay, to answer that, first I have to say that quantum information science is actually more than one field. It consists of things like quantum sensing, quantum communication and networking, quantum computing, which we'd already mentioned. And all of these things have critical relevance to the Army. For example, quantum computing is good for logistics and optimization problems that DoD deals with all the time. Sensing for electromagnetic radiation, for electric and magnetic fields, and for gravitational fields even, for example, to find underground structures and tunnels. And then there's inertial sensing, which quantum can also do. And that means inertial sensing means measuring accelerations, rotations, and combining that with gravity and time to find out where you are in order to navigate and find your position. And that basically augments GPS and allows you to operate in GPS-denied environments. So many of these sensors are based on what's called atom interferometry. That's what makes them quantum. It exploits a property of quantum mechanics where everything is waves. Atoms have wave-like properties. So it's the equivalent of optics, but you're interfering atom waves here. And then in addition to these sensing and computing applications, there's quantum networks. And first let me say, quantum networks are not replacements for ordinary networks. I should say that more generally, that quantum things in general are not replacements for classical things. Like a quantum computer will never replace a classical computer. It's good for very specific problems that a classical computer, for example, can't solve well, and a quantum computer can. So similarly, you'll need classical networks. They're never going to go away. You need them to distribute ordinary information. A quantum network, on the other hand, distributes entanglement. What that can do is it can allow for more secure communication, for one thing, but it actually has many other applications that are probably more important in many ways. It allows for the distribution of time, for example, that's intrinsically synchronized, since the time information that's shared across the network is coherent. So that means that in a sense that the network itself is a single clock. So instead of having to do time transfer where you lose information, the whole clock is the network. It also allows for distributed sensing. The network will allow for distributed sensing in a way that you can combine the information across the sensors coherently, and in that way you can extract information that wouldn't be available classically, and also at a higher sensitivity. And you can combine quantum computers. If you have in the future quantum computers, you can make a network of quantum computers that will be more powerful than a single computer. So all of these are ways that quantum information science will impact multi-domain operations.
Excellent. Thank you for clarifying. Across the Army, there are fewer than 50 senior research scientists, known as STs, who serve as general officer equivalents, advising leadership on science matters. What do you see as the best practice for the ST community as a whole? And what are you as a research leader doing to help make the Army of the future stronger through the physical sciences?
I think the STs need to be understood by the Army as a resource, as a source for very deep expertise across science and technology domains. I don't think that they're widely recognized nor widely used by the Army. There's some pockets within the Army that do that. They seek us out, but it remains largely in our own organizations. So as things stand, we actually have to be very proactive in order to get people to seek us out to answer scientific questions they have. More often than not, they'll go seek outsiders. They'll go to the National Academy or other outside groups for reviews. They have this big body of expertise in-house. It's not big. It's actually only about 40 currently, not 50. To your question of how do I help make the Army of the future stronger through the physical sciences, I think it's by discovering new opportunities and new directions well before they're recognized by others, and certainly well before they're recognized as having an Army or a DoD relevance, and pursuing those ideas, really pushing at them. My experience with quantum information science, I was supporting it for 3 decades. That's emblematic of that. It's now, as I said, widely recognized as an Army priority research area, and even through legislation as a national quantum initiative. But 30 years ago, it was just this budding scientific idea. So you have to carry these ideas forward and be very visionary in terms of seeing the things that are going to have this kind of long-term impact.
How do you think that the ST community helps to make America's Army stronger?
Well, as a community, we do this in a range of scientific and engineering disciplines because each of us is an expert only in a portion of that full spectrum of S&T. But together, we have a body of expertise that's capable of modernizing the Army in transformative ways. So we envision the future in our area of S&T. And in that way, we can prevent technological surprise. Better yet, we can create technological surprise for our adversaries. And I think that's even more important.
In your current role as the ST for physical sciences at the Army Research Office, how do you think we're doing making new discoveries, pushing the boundaries of science and technology for future American soldiers?
I think we're going strong. Across ARO, I see a constant flow of novel, potentially transformative scientific ideas. They're just waiting to turn into the next laser. And I bring that up because the laser itself was a product of early ARO grants in the 1950s. I see lots more like that to come.
Dr. Peter Reynolds, the Army Senior Research Scientist for the Physical Sciences. Thank you for taking time to speak with me today.
Thank you very much. I enjoyed it.
Well, thanks for joining us for What We Learned Today. In upcoming episodes, we'll continue the discussion about the underpinning research that will build the Army of the future. Please consider liking and subscribing. Science is a journey of discovery, and we're glad you're along for the ride. For the Army Research Lab, I'm Tracy Dean.